Mathematical decision making, network models, Euler paths and circuits. Lesson 3 for Edmeadow Group. The learning goals for Lesson 3 are for you to identify and model Euler path and circuit problems, understand the meaning of basic graph terminology, and classify which graphs have Euler paths and Euler circuits using Euler's theorems. We'll begin Lesson 3 with a brain activator. Draw figures 1 through 4 on your paper. Which diagram can be traced without lifting your pencil and without retracing any lines? You will want to pause the video to work on these. A quick check for 1 through 4 shows that problem 1 is impossible. Figures 2, 3, and 4 can be traced by starting at a vertex and going over each of the lines only once. If you missed one of these, pause the video and try it again. Let's look at how you might have traced 2, 3, and 4. Notice that I've labeled the edges with numbers to indicate the path that I have taken. Further, I've also put arrows on the edges to indicate the direction in which I traveled. For example, in problem 2, I started at the bottom left edge. The arrow indicates the direction I traveled. The numbers indicate the order in which I traveled. And as I go through each of these edges, you'll see that finally I have traced this diagram. Similarly, I started at the left on number 3 and traveled through a path that allowed me to trace the figure. With 4, I started at the top vertex and went down to the left as I traced through the edges. This is one method that you can indicate a path when you have a particular figure that is traceable. Those are just the ways that I did problems 2, 3, and 4. There are other ways to do it as well. Now I want you to draw figures 5 through 8 on your paper. Which of these diagrams can be traced without lifting your pencil and without retracing any lines? You will want to pause the video to work on these. A quick check of these problems indicates that only one of the figures is not traceable. Number 6 is impossible. The others have paths that can be taken. If you missed one of these, pause and try it again. Looking at the way these were solved, you'll see that I've used again the numbering system with the arrows to indicate the path I took as I traveled through the figure in order to trace it completely. Again, there are other ways to do it as well. Well, how does all this relate to what we were talking about earlier with our goals for this particular lesson? Well, it actually has to do with an ancient problem, an old problem that puzzled the citizens of Quinesburg for a long time. Quinesburg was one of those towns that was located on a river. It was very fortunate for the town that it was, because it allowed the town to grow and flourish. In the 1700s, the townspeople were able to build bridges that connected land masses in the city. For you see, the river actually going through the city separated the banks, the two sides of the city, as well as created islands out in the river itself. The citizens built 7 bridges to connect the land masses. Here you see the islands are labeled A and D, and the two sides of the riverbank are indicated with B and C. And 7 bridges have been placed in approximately the places they existed at that time. The city is still in existence. It's now in Russia, and it has a different name, Kaliningrad. The people of Königsberg decided that this was a beautiful city. They enjoyed on Sunday afternoons taking strolls through the city itself and going over the bridges to the islands. Now, young couples especially enjoyed this Sunday afternoon pastime, and soon it became a game to see if it was possible to travel over each of the 7 bridges only once and to visit each of the land masses. So, it's very similar to the kinds of problems that you were doing earlier. Is it possible to find a way, a path, that would connect these particular points while only going over certain edges, and each edge once? Well, try as they might, the citizens were unable to come up with a path that would work. But they weren't sure if it truly was impossible or if the solution eluded them. And so someone wrote to Leonhard Euler to find out if he knew whether or not it was possible, and if it were impossible, could he prove that that was the case. Now, Leonhard Euler was a Swiss mathematician and physicist, and he was one of those rare individuals who was remarkable in many ways. He wrote over 500 works in his lifetime, but many of his works continue to be published today and are being studied because he wrote numerous letters to other scholars of his day. He wasn't just devoted to mathematics. He was a people person too, and I imagine that's why this person contacted Euler to see if he could figure out the answer to this, it's seemingly trivial problem. I mean, it's not something that was of vital essence to the lives of the people who lived there, but they were just curious. And so Euler set about to figure out whether or not it was possible. And through this particular problem, he invented the idea of a graph, and he was able to solve it. We're going to look at Euler's theorems and apply them today. First, let's look at some definitions so that we know the terminology that's being used. A network graph has points, which I've been calling vertices. In some textbooks you may see them referred to as nodes. And they also have edges or sides. In some textbooks those are referred to as lines, even though they don't have to be straight, as we have studied in geometry, or as we've thought about that term in geometry. Each object in the graph is represented by a vertex. So an object could be a computer, or computers in this case. There'd be 5 of them. Or it could be houses, mailboxes, parking meters, number of different things. And then connections between the objects are shown by the edges or the sides. So if these were computers, we may have cables that are connecting computer A to computer B. These are houses. That might be a path or a street that connects house A to house B. If we're talking about mailboxes, that might be the path that the mailman takes as he moves from mailbox A to mailbox B. And finally, each edge in a graph joins 2 distinct vertices. So notice that each edge has at its endpoints 2 very different vertices. Let's look at how we can apply this definition. So use the definition. Look at these 2 figures. Is the figure a graph? Explain why you think that it is or is not. For the figure on the left, we would say that yes, it is a graph. It meets the definition. Each object in the graph is represented by a vertex. The connections between the objects are shown by edges, and each edge joins 2 distinct vertices. On the right, we would have to say that no, it's not a graph. We do have vertices here. We do have edges, but notice that one of the edges in the diagram joins a vertex to itself. So it fails this part of the definition. Each edge joins 2 distinct vertices. So there are 2 connected sides. 2 is an even number, so we would say vertex A is an even degree vertex. B is very similar. There are 2 connected sides, so therefore B is an even degree vertex. C is also an even degree vertex, but D is odd. Notice that D is connected to A, D is connected to C, and D is connected to E. So it has 3 connected sides. So we would say it is an odd degree vertex. Similarly, E is an odd degree vertex because it is only connected to D, and 1 is an odd number. These numbers are called the valence. The valence of a vertex in a network is the number of edges meeting at the vertex. We also know that a graph might be traversable or it might not be. A graph is traversable if you can trace the shape without lifting your pencil and without going over a side more than once. So this is similar to the brain activator that we used earlier. Notice in this particular graph we have 4 vertices, A, B, C, and D. We have several edges. In fact, A is connected to B in multiple ways and D in multiple ways. And then we have other edges as well. So for this particular graph, we have 8 edges. So this graph will be traversable if we can start at a vertex and go on each of these edges exactly once and completely trace the figure. Is it traversable? And the answer to that is yes. In this particular case, I have marked the path that I've gone through this particular graph using the arrows and the numbered edges. Notice that I've also indicated the way that I could go through the path to trace the graph by using the letters. So starting at C, I went to A, then D, back to A along a different edge, then to B, then to A along a different edge, back to B on a different edge, to C, and finally to D. So each of those vertices are listed in the order for the path that I took. Again, you may be able to show this in multiple ways. Is there a way to predict whether or not a graph is traversable? Does it have a path? Is it possible to trace this particular graph without retracing any of the edges or lifting your pencil? And that's the essence of the Königsberg bridges problem. Is there a way to determine? Well, it turns out we could just continue to work on this to figure out, is there a way? And again, I didn't show the arrows and the numbered segments for this particular one, but I've listed the vertices in the order which I took a path through the figure, and decided that yes, because I was able to trace all of the edges without retracing any, that it was traversable. But could we just look at a particular graph to determine whether or not it's traversable? It turns out this one's not, but we might spend a good bit of time and effort to figure out whether or not it is. And the same is true for this one. We could spend a good bit of time with it trying to decide, is it possible to have a path through this graph? It turns out that it's not. And a way that we can determine that quickly is by applying Euler's path theorem. Euler said that for a shape to be traversable, we had to have one of two conditions. Either all the vertices are of even degree, or exactly two vertices are odd and the rest are even. So going back to those four examples that we've just looked at, notice that for the first one, if we looked at vertex A, there are 6 edges that join at A, so A is even. B is also even because there are 4 edges that join there. C is odd because it has 3 edges. And D is also odd because there are 3 edges. Remember that the word that we use for that is valence. So we could say that A's valence is 6, the valence for B is 4, the valence for C is 3, and the valence for D is also 3. So in this case we have 2 odd and 2 even. So that is, according to Euler, one of the conditions that would make this particular graph traversable. So just knowing the how many even and odd vertices we have would help us make that determination without having to do multiple tries to see if it's possible. Let's look at the second one. We said it was traversable. Notice that it also fits with Euler's theorem. each of the vertices in this diagram is even. And so we know that it is traversable. All of the vertices are of even degree. For the third one and the fourth, we said those were not traversable. Notice that for the third one, there are 4 odd and 3 even. And that does not meet the condition of all vertices are of even degree. It does not meet the condition that exactly 2 vertices are odd and the rest are even. And finally, for our last example that we had, 6 are odd and 2 are even, and again, does not meet the conditions. So we could have a very complicated graph, and we would be able to determine very quickly whether it was traversable or not without ever having to actually come up with a path. Now we do refer to the path that's taken through a particular figure as the Euler path, and we've already talked about how that can be labeled in different ways. Let's go back to the bridges. Again, there are 4 land masses, so I've represented each of the 4 land masses as a vertex because our vertices represent objects. So our vertices are A, B, C, and D in this case. Then the paths over the bridges are the sides of the network. So if we just find the degree of each vertex, then we should be able to determine whether or not this graph is traversable. How many edges connect at A? How many connect at B, C, and D? As we look at that, A has 5 edges, B has 3, C has 3, and D has 3. So what do you think Euler told the people of Königsberg? Is this particular graph traversable? In other words, is it possible for a young couple out for a Sunday evening stroll able to go from one landmass to another by going over each of the bridges exactly once? And the answer was no, it's impossible. Now, we're not actually going to prove this, we're just going to use Euler's theorem. Because we know that all 4 are odd, that does not meet the condition that all of them are even, or the other condition being that exactly 2 are odd and the rest are even. So we know that it is impossible that we had earlier. Notice that these edges are all connected, so we know that that meets that condition. And then as you look at the vertex A, it has valence 2, B has valence 4, C has valence 4, D has valence 2, E has valence 4, F has valence 4, and G has valence 4. So all of them have a degree that's even. Every vertex is even. So it meets the conditions, and we know that it has an Euler circuit, at least one, and it usually has more. Can you find others that would work? That's just one. Now, why is this all important? It seems like the Königsberg Bridge problem was just something that people were doing as a pastime, sort of recreational mathematics, if you will. Well, it actually turns out that the graph theory that Euler developed has helped with management science. Operations research, which is also called management science, is the part of mathematics concerned with efficient operations of business and governments. So if you think about it, you wouldn't want your mailman to, even if he's not walking from house to house but riding in one of those little carts or in his own car, going from point A to point B to point C and then back to point B, unless it were necessary for the to conduct business. Now, if he does a lot of repeating, then he's wasting time and he's wasting gas, and all of that equates into money. And of course, governments are very concerned about efficiency and wanting to make sure that they are using taxpayer money in an efficient manner and being effective with it. Likewise, industries are concerned about that as well. So this sort of study is applied to routing problems and cost minimization, just to name a few applications. You're going to work on a few exercises that will apply some of the things that we've touched on today. If you need to, you can review any part of this video to assist you as you complete the assignment.